Welcome back. It is day 2 of our crash course. Yesterday you learned how to look at a system from outside, the actors, the boundary, the context. Today we open the box. Today is about building blocks. The Lego pieces every modern application is made of. By the end of today you will know what an API is, what a database is, what a cache is, and most importantly, when to use which one. We will also learn to draw the next level of diagram, called a container diagram. That is C4 level 2. Today is going to be the most technical day of the week. There is a lot of new vocabulary. Take it slowly. Take notes. If something does not click, ask in the cohort channel. Every senior engineer struggled with these same names at the start. Just to anchor where we are. Yesterday you learned 5 words: system, component, boundary, actor, interface. You produced a context diagram, a user story set, and an ambiguity log for LearnLanka. Today we zoom in. Yesterday's context diagram showed your system as one box. Today we open that box and look at the building blocks inside. Same diagram method, C4, just a different zoom level. If you have any questions about day 1, hold them for the cohort retro on Friday. For now, follow along. Today's content builds directly on yesterday's. 5 concrete skills by the end of today. 1. Trace a request from a phone all the way through to a database, naming every hop. The mental model is more important than any one hop. 2. Design a small REST API. Resources, verbs, status codes, pagination. The 4 things that make an API readable and predictable. 3. Pick the right storage. Relational, document. Key value cache, object store. Each has a sweet spot, and we will give you a 1-page cheat sheet. 4. Apply caching, queuing, and statelessness. 3 patterns that make modern systems fast and scalable. We will explain each from first principles. 5. Draw a container diagram, C4 level 2. The picture you would show a fellow developer to explain, this is how my service is built. That is the day. Before we name each block, here is the journey. When you tap a button on your phone, a small message travels through 6 or 7 different places before you see anything new on screen. It starts on your phone in the app. The app forms a request, usually a small piece of JSON text plus some headers. It calls a service over the internet. Stop 1. DNS. The domain name system. Like a phone book. Your phone says where is api.bookswap.lk and DNS returns an IP address. Stop 2. TLS encryption. Once you have the address, you open a secure connection. TLS is the lock. Stop 3. The load balancer, the receptionist at the building's entrance. It picks one of many available servers behind it and routes your request there. Stop 4. The API service. Your business logic runs here. It might also call a cache, a database, a queue, or a blob store to do its work. After that, the response retraces the same path back to your phone. The whole journey, ideally, finishes in under a second. We are going to look at each stop, one slide at a time. Let us start with DNS and TLS, the first 2 stops. DNS is the phone book of the internet. Computers actually talk to each other using IP addresses, which are numbers like 51, 20, 30, 40. But humans cannot remember numbers, so we use names api.bookswap.lk. DNS translates names into numbers. When your app calls api.bookswap.lk, it first asks DNS, what is the IP address? DNS answers. Your phone caches the answer for a few minutes so it does not have to ask again every time. TLS is the second stop. It stands for Transport Layer Security. It is what creates that little padlock you see in your browser. TLS does 2 things. It encrypts your data so other people on the same network cannot read it. and it verifies you are talking to the real server, not an imposter pretending to be one. Every modern application uses both. You usually do not have to think about them, they are configured once and forgotten. But when something breaks at one of these layers, the symptoms can be confusing. Hence, you should know they exist. Stop 3. The load balancer. Imagine an office where one receptionist welcomes everyone, decides which empty desk they should sit at, and skips desks where someone has gone on lunch. That is a load balancer. A real backend never runs as a single server. It runs as several copies behind a load balancer. The load balancer keeps an eye on which copies are healthy. When a request comes in, it picks one healthy copy and routes the request there. This is what makes scale possible. When traffic spikes, say BookSwap is featured in the newspaper on Sunday, you add a 4th or 5th or 10th copy of the service. No code change is needed. The load balancer just routes the new traffic to one more desk. The load balancer also handles 2 other useful things. It ends the TLS encryption so each backend copy does not have to, and it can rate limit abusive callers. In Azure, this is Azure Front Door or Application Gateway, or just the built-in load balancer in Azure App Service. Stop 4. The API service. This is where your code runs. The API service does 3 things in order. It receives an HTTP request. The request has a verb like GET or POST, a path like /books, and possibly a body containing JSON data. It decides what to do. Maybe it reads from the database. Maybe it calls another service. Maybe it applies validation rules. Maybe it calculates a result. This is your business logic. It returns a response. A status code that tells the client what happened, and usually a JSON body the client can use. That is it. Receive, decide, respond. The API service is the brain. Most of the code you will write in your career lives here. The other building blocks support it. The database is the source of truth. When the API service needs to read or write durable data, it talks to the database. Durable means survives a power cut. Once you write something to the database and it confirms saved, that data will still be there tomorrow. The database is reliable in 3 ways. It saves writes to disk before saying OK. So a power cut does not lose your data. It is backed up. Daily, sometimes every hour, sometimes continuously. You can restore yesterday's state if something goes wrong. It is the source of truth. If 2 parts of the system disagree about a value, the database wins. The cache, the queue, anything else, they are all secondary. The database holds reality. There are different kinds of databases: relational, document, key value. We will look at each in a few slides. A cache is fast, but it is not the truth. A cache is an in-memory store. It holds copies of data that the system reads often so that the database does not have to be hit for every read. 2 important properties: fast. Reads from a cache happen in less than a millisecond. Reads from a database might take 5 to 50 milliseconds. That is the trade. Volatile. Cache data lives in memory only. Restart the cache machine and everything in it is gone. That sounds bad, but it is fine. The database still has all the real data, and the cache rebuilds itself the next time it is asked. You use a cache for things that are read many times faster than they change. The popular book detail page on BookSwap. Tutor profiles on LearnLenka. The most viewed product on an e-commerce site. Things where being a few seconds out of date is okay. The most common cache is Azure Cache for retries, or just retries on its own. A message queue is a buffer for asynchronous work. Imagine a conveyor belt in a factory. One person drops items on the belt. Workers pick items off the other end at their own pace. The dropper does not wait for the worker. The worker does not wait for the dropper. They are decoupled in time. That is a queue. When the user submits a contact form on a website, the web service does two things. It saves the form to the database that has to happen before the response, and it puts a job on a queue, send confirmation email to this address. The web service immediately returns form received. The email worker picks up the job a few seconds later and actually sends the email. The user did not wait for the email server. If the email server is slow today, the user does not notice. If it is broken, the email worker retries until it works. A queue is also how you absorb traffic spikes. If 10,000 emails need to be sent after a marketing campaign, the queue holds them. Workers drain the queue at a steady pace. No matter how big the spike, the user facing a PI returns instantly. In Azure, this is Azure Service Bus. There is also Azure Storage Queue for simpler cases. The last block, the object store. Files are different from rows. A book photo is 2 megabytes. A PDF invoice is half a megabyte. A short video is 50 megabytes. Putting these inside a database makes the database huge, slow, and expensive to back up. So we put them in an object store instead. An object store is built for files. You give it a key like book/ISBN/9,780,143,036,555.jpg, and it stores the bytes. You ask for the file by key and it gives you the bytes back. 3 reasons it is great: cheap, pay per gigabyte stored, much cheaper than putting files in a database. Designed for files. No queries, no schema, just keys and bytes. Serves directly. The object store can hand a file to the user with a signed link. Your API never sees the bytes. That keeps your API light. In Azure, this is Azure Blob Storage. The other big one is Amazon S3. Pause and look at this table. It is the most important slide in day 2. These 7 names cover almost every backend you will see in your career. Client, the thing that talks to your API, mobile, web, or another service. Load balancer spreads traffic when you have more than one copy of a service. API service, your code, where business rules live. Database, the durable source of truth. Cache, a fast, lossy copy. Queue, buffers asynchronous work. Object store, for files. Whenever you sketch a design, start by listing which of these you need. Most small applications need 4 or 5. The big systems use all 7, often several of each. Memorize the names. Memorize what each one is for. The whole rest of the day is about how to use them well. Now let us spend a little time on the API itself. Most APIs today follow a style called REST. REST is just a set of conventions for how an HTTP API should look so that any developer can pick it up and use it. 3 conventions. Resources, the things you can act on. In BookSwap, books, members, loans, requests. Each resource gets a URL, verbs. HTTP methods, GET to read, POST to create, PATCH or PUT to update, DELETE to remove, status codes, a 3-digit number on every response that tells the client what happened. We will see the 8 you must memorize in 2 slides. If you follow REST conventions, your API is predictable. A new developer can guess most endpoints from a list of resources. That is the point. This is the single mistake junior developers make most often when designing REST API is. They put verbs in the URL, POST to /createbook, POST to /updatebook/123, POST to /deletebook. They name every endpoint as if it is a function call. Stop. The verb is already in the HTTP method. Use nouns for the path. Books is a noun. POST to slash books to create. PATCH to slash books slash 123 to update. DELETE to slash books slash 123 to delete. GET to slash books to list. Same noun, different verbs. This makes a P is tiny. You learn one resource and you know how to read, create, update, delete it. There are no surprise endpoint names. This is the most consistent style across the industry. When you see verbs in someone's URLs, that is a sign they are new, or that the API was designed in a hurry. Every HTTP response has a status code, a 3-digit number. The first digit is the family. Memorize these. 2XX means success. 200 means OK, your GET request worked. 201 means created, your POST created a new resource. 204 means no content, succeeded, nothing to return. 4XX means the client made a mistake. 400 means bad request, your input was malformed. 401 means unauthorized, you need to log in. 403 means forbidden, you are logged in but not allowed. 404 means not found, the thing does not exist. 5XX means the server made a mistake. 500 is internal server error, our problem, not yours. If your API returns 200 for everything including failures, you are doing it wrong. Use the right code. Clients depend on it, especially mobile apps and retry logic. They read the code first, before looking at the body. 2 more API rules. Both are easy to forget, both bite hard in production. Rule 1. Always paginate list endpoints. Never return all books in one response. There might be 50,000. Use page and page size parameters. GET/books with page equals 2 and page size equals 20. Return a total so the client knows how many pages exist. Without pagination, your server runs out of memory and your phone runs out of patience. Rule 2. Make endpoints that move money idempotent. Idempotent means same input, same effect, no matter how many times you call it. If a POST charges a card, the client might retry on a network glitch. Without protection, the customer pays twice. The fix is to accept an idempotency key header. Same key, same result, no double charge. Networks lose packets. Mobile networks lose them often. Designed for retry from the start. Now let us look at storage choices, starting with the relational database. A relational database stores data in tables with rows and columns. Each row has a fixed shape, same columns as every other row. Tables can refer to each other through keys called foreign keys. The query language is SQL. You write things like select star from books where condition equals new. SQL has been around for 50 years. The tooling is mature, every team knows it. Examples: Azure SQL, PostgreSQL, MySQL, best for data with clear shape and relationships, orders that have line items, members who have loans on books, invoices linked to customers. Anywhere you need transactions, multiple changes that must succeed or fail as a group. This is the default choice for most business applications. When in doubt, start here. Move to something else only when you have a specific reason. A document database stores data as JSON documents. Each document can have a different shape. There is no fixed schema enforced. You can have one user profile that has a phone number, another that has an email address, and another that has both plus a list of preferred subjects, all in the same collection. The database does not complain. Examples: Azure Cosmos DB, MongoDB, DynamoDB, best for data with flexible or nested shape, a product page where features vary by category, a user profile with arbitrary preferences, a review that may or may not have photos attached, easy to evolve. When you add a new field, you do not need a database migration. Old documents simply do not have the field new ones do. Your code handles both. The trade-off: joins between collections are clumsy. Transactions across documents are limited. If your data is highly relational, stay with a relational database. A key-value store is the simplest kind of database. You give it a key, it gives you a value. That is the whole interface. The most common one is retries, also known as Azure Cache for readies. Readies lives in memory, so reads happen in less than a millisecond. Examples of what to store in it: user session tokens, so you do not hit the main database on every request. The most popular pages or products. Counters for rate limiting. This IP has made 100 requests this minute, slow them down. Leaderboards. Anything where reads happen many times faster than writes. The trade-off: volatile. Restart readies and it is empty. So always have a database behind it. The cache makes things fast. The database makes things permanent. We mentioned object stores. Let me give you a few more details. An object store is the cheapest place to put files. You pay per gigabyte stored per month and per gigabyte of data served. For most BISTEC scale applications, that is small change. Examples: Azure Blob Storage, Amazon S3, Google Cloud Storage, Best for user-uploaded photos, PDF invoices, short video clips, generated reports, database backups, anything binary that is more than a few kilobytes. The rule is: never store binary data in your database. Database backups become enormous and slow. Cloning a database for a developer to run locally takes hours. Performance suffers across the board. Files belong in the object store, with a URL stored in the database pointing to them. A search engine is a specialized store for full-text search across many fields with relevance ranking. A relational database can search, It can filter rows where the title contains a word, but it cannot rank by relevance, putting better matches first. It cannot handle typos. It cannot handle synonyms, phone matching mobile. A search engine does all of those very well and very fast. Examples: Azure iSearch, Elasticsearch, OpenSearch. Best product catalogs, job listings, tutor profiles, anything where users type a free text query and expect best match first with typos handled. The pattern: the database stays the source of truth. The search engine is a derived index, kept up to date by a background job. They cooperate. The last data store on our list: the event stream. An event stream is an append-only log of events. Many consumers can read the same stream at their own pace and replay it later if they need to. Examples: Azure Event Hubs, Apache Kafka, Best for audit logs, order events, click streams. Any case where multiple downstream systems care about the same event. For example, an order placed event triggers shipping, billing, marketing, and analytics, each in a separate service. The difference from a queue: a queue delivers each message to one consumer. A stream lets many consumers read independently, each at their own pace. You will not need an event stream for most simple applications, but you will see one in every large business system. Here is the one-page cheat sheet. Print this, pin it next to your monitor. Relational data with joins: pick a relational database. Flexible or nested shape: pick a document database. Hot session or counter that lives in memory: pick a key-value cache. Files, photos, videos: pick an object store. Full-text search and ranking: pick a search engine. Append-only events with replay: pick an event stream. When you are designing, walk through the data your system holds and match each piece to the right store. Most systems use 2 or 3. Big systems use 4 or 5. Now let us walk through the most common way to use a cache. It is called the cache-aside pattern. 5 simple steps. 1. A read request comes in. Your code checks the cache first using a key like book:42. 2. If the cache has the answer, a cache hit, return it. Done. Sub-millisecond. 3. If the cache does not have it, a cache miss, read from the database. 4. Store the result in the cache with a time to live. For example, 60 seconds. After 60 seconds, the cache entry expires and the next read will refresh it. 5. On every write, update the database first and then delete the cached entry. The next read will see no cache, hit the database and repopulate the cache with the fresh value. That is it. Cache aside. You will use this pattern many times in your career. Memorize the 5 steps. 3 classic signs that work belongs on a queue and not in the request itself. Sign 1. The user does not need the result now. Sending a confirmation email, generating a PDF report, resizing an uploaded photo. The user has clicked submit and moved on. The work happens in the background on a worker while the user is doing something else. Sign 2. The work might fail. Calls to external services often fail transiently. The email server is overloaded. The payment gateway has a hiccup. A queue lets a worker retry several times before giving up. The user is not waiting for those retries. Sign 3. The work has spiky load. If 10,000 emails need to be sent after a campaign blast, putting them all on a queue absorbs the spike. The API returns instantly. Workers drain the queue at their own pace. No matter how big the spike, the user-facing experience stays snappy. If your design has any of these 3 signs, reach for a queue. Now the last big idea of the day, statelessness. A service is stateless if it remembers nothing between requests. Every request comes in with everything it needs, usually a token that identifies the user. The state lives elsewhere in the database, the cache, the token itself. Why this matters? Stateless services scale beautifully. The load balancer can route the next request to any copy. Want to handle 10 times the traffic? Run 10 times as many copies. No code change. The common mistake: storing user sessions in memory. Caching results in a local dictionary that only this one server has. Holding open file handles between requests. All of these break statelessness. Here is the test. Imagine you killed any one copy of your service right now. Would users notice anything other than mild slowdown? If yes, your service is not stateless. Find what state it is keeping locally and move it to a shared store. This single idea is what makes modern cloud applications scale. Now you put all of it into practice. Today's challenge is called BookSwap. The brief: BookSwap is a small marketplace where neighbors in a Colombo apartment block trade or lend books with each other. Members can list books, search the catalog, request to borrow, and rate each other after the loan. Photos, a weekly digest email. The whole product is shipped in 6 weeks. Your job is to design the backend. REST API, storage choices, where you use a cache or a queue and a container diagram. You will not write code today. This is a design exercise. You produce a spec another developer could implement. You have about 50 minutes in hour 3. Do not aim for perfection. Aim for clear, defensible choices. Same shape as day 1. 4 deliverables, 25 points each. Pass mark 75 out of 100. Full rubric in challenge.md. Deliverable 1. The Open API spec. Resources, verbs, status codes, pagination. The contract another developer would code against. Deliverable 2. Storage decisions. For each data type, your chosen store and why, including why not the alternatives. Deliverable 3. The container diagram. C4 level 2. Web app API database cache queue blob store. Sync versus async paths shown distinctly. Deliverable 4. The mock smoke test. Use Prism to mock serve your spec, run 5 sample requests, and write up your findings. 3 free tools. Install them before Hour 3 starts. Swagger Editor, a web-based editor for open API specifications. You paste your spec on the left, you see it rendered as documentation on the right, validation as you type. Free, no sign-up. Just go to editor.swagger.io. Prism, a mock server for open API files. You run a single command, npx at stoplight/prism mock your spec, and you have a fake API you can call. Postman or Bruno. Both are free. They send HTTP requests and save them in collections. Use them to call your Prism mock and check the responses. These 3 tools take 5 minutes to set up and save you hours of writing test code. Solid day. You learned the 7 building blocks. You learned REST conventions, status codes, pagination, idempotency. You learned cache-aside, async queues, and statelessness. Tonight, 6 things to lock it in. 1. Read the Microsoft Learn pages on the cache-aside pattern and on throttling. 2. Add a paragraph to your decision doc about retry policy on 5xx errors. 3. Find a public BISTEC product API and rate it against today's REST checklist. 4. Try Bruno or Postman against jsonplaceholder.typico.com and save a 5-request collection. 5. Reread your open API file in the morning. Fix anything that feels awkward. 6. Add 2 questions about queues to your learning log.md. Tomorrow, day 3 is about quality. How fast, how reliable, how secure. With real numbers. See you at 9.